Okay. Should be good. Okay, so let's welcome our second speaker. Sofya, I think it's going to be very difficult for me to pronounce your surname. And she's from India, and she is a PhD student. And her research mainly focusing on the improving network training on the data, which comes from the physics simulation and the PDS. Let's welcome her.
Thank you. Okay, hi everyone. My name is Sofya. Thank you for presenting me. It's a work with my advisor, Bruno Rafan, who is here, and also our colleague, Abhishek. Yeah, the title is pretty long, so simply speaking, our work, our paper I present, focused on training of expressive surrogates with less simulations. And first, to narrow down the area of AI4Science we work on, training surrogates for AI4Science, let me explain what surrogates are, or repeat what surrogates are, and what is the problem with them. As an example, consider physical phenomena of launching an arrow with a bow. It is described with the projectile motion equation. And with a numerical solver computer, we can discretize time and make it solve linear equations, and step by step, we will acquire the trajectory of the arrow motion. We can as well change the input parameters of the simulation. Here it is angle. You see the changing angle and how the trajectory changes, and the speed, the red one. So it is the initial conditions as well. It can be changing boundary condition, equation coefficients, making it a multi-parametric simulation. Such tasks as sensitivity analysis, design space, exploration, and optimization, and example forecasting, like in climate prediction that was discussed in the first keynote talk. These require execution of thousands and even millions of simulation instances across many different parameters. And these large-scale ensemble runs are compute-intensive. One way to alleviate this burden are neural surrogate models. So surrogate approximates simulation model, producing computationally faster trajectories in trade for accuracy, since it is an approximation. And these make large-scale ensembles runs much more feasible. Well, that is great, right? But we have to train the neural network first. So training a neural network, supervised training neural network, is usually performed in an epoch-based manner, because there is usually a data set given. In our unusual case of supervised surrogate, we don't necessarily have a data set, but we have a solver which can create the data. So first we have to create a data set. Using the solver, it aims to substitute, and only then perform the training of the neural network by iterating over this data set over and over, epoch-based training. And we refer it as offline training. Let's take a closer look to understand with what price it comes. So as I said, first we want to create the data set, which we will have to store on disk, which is expensive storage. We randomly choose simulation parameters as much as we can store within the compute budget. Randomly because its creation of the data set is before the training, happens before the training. We don't have any information about training or the simulation distributions. And then solver calculates trajectory one by one, and when finished, writes this large simulation on disk, which is a costly input operation, and solver has to wait. And when we finish generating the dataset, we can start training the neural network. And during the training, the simulation data has to be read from disk, and training process has to wait again, because the operation is costly. With these issues in mind, offline training is IO-bound task. Then it is inefficient on HPC systems and not scalable to bigger simulation applications if it's trained offline. But do not lose hope in surrogates just yet, because next I'm going to present to you the online training. I'm going to present online training of surrogates that bypass storage without worsening surrogate quality. We call training online when it is performed in parallel to the creation of the data. can also be referred as in situ, stream-based, event-driven. Let's take a closer look. We have M solvers executing in parallel independently. When the solver is available, it runs a simulation job with the input parameter from the queue, which length is predefined by the compute budget N. And we have a process that trains a neural network with the data that is stored in a buffer, in a RAM. And it creates the badges from it and able to do the optimization process. As the solvers run simulations independently, as soon as the trajectory step is calculated by one of the solvers, it is sent to the main process. And if the buffer is full, in order to receive the new time step sample, we have to delete some older sample. Overall, by eliminating need of storage and I/O issues with it, data stream is limited only by compute budget, N, which makes it a compute-bound task. And surrogate training becomes more efficient on HPC system. And we have an open source HPC framework called Melissa, developed by our team, which takes care of orchestrating this whole system of online training. It is scalable thanks to concurrent simulation executions and distributed both neural network training and simulation execution. It is elastic as it adapts to resource availability on the HPC cluster, and it is fault tolerant. The last year conference paper, the experiment of training a surrogate for heat equation was conducted and has shown that online approach is much more I/O efficient than offline. First of all, amount of data seen by neural network, almost 100 times more, but we didn't need to store all these 8 terabytes of data. And the throughput of samples during training is 10 times higher, so neural network training process was not slowed down by the I/O bottleneck. As well, it shows better neural network performance, since number of unique simulation parameters was almost 100 times more. But that is not all for the advantages of online training. Melissa opens up ability to dynamically control data creation, since we have this queue of waiting jobs to be executed with the parameters we have in a queue. So it is possible to sample simulation parameters in a way to adapt to the neural network training dynamics and needs, and we call it adaptive sampling. So our paper contribution of this workshop is advancing Melissa framework with developed adaptive sampling method named BRID, which goal is to train a better surrogate within compute budget and what is called data efficient training. Main approach to data efficiency in deep learning is active learning. Initially, it is applied for choosing subsets of unlabeled finite datasets in order to label them with the help of a human, for example. Basically something that has a high cost of labeling when there is a lot of unlabeled data. The goal would be to label as little data as possible while training a better model. It would use uncertainty quantification, similarity-based metrics, and many others. Other works are developing adaptive sampling of collocation points for physics-informed neural network spins in order to train the surrogate in less iterations. But these are based on residual loss, which doesn't require any simulations to be run at all. Our work, in contrast, is focused on developing active learning methods that choose simulation parameters from infinite space opposed to finite datasets, since the range of the input parameters theta is some interval. And solvers has to be executed because their network is supervised, like neural operators, for example, or diffusion models, opposed to data-free pins. And we have only some data available in the buffer because of this streaming online approach. So the approach we proposed based on assumption that there need to be more parameters to be sampled where the neural network loss is high. To do that, we treat loss landscape of the neural network, so associated with the neural network weights, but over the theta, over the simulation parameters as a distribution, p theta. But this distribution doesn't have an explicit form, so we cannot directly evaluate the distribution or sample from it. We can only do that if we choose the input parameter, run the solver, get the data, train the neural network, and get the loss. So instead we use important sampling method, which builds an approximate distribution of a known form, more explicit form, that is easy to sample from and evaluate as well. Our important sampling method is based on a renowned population Monte Carlo technique proposed by Olivier Capet in 2004. Let's take a look again. We have initial points, theta I, or parents' population, each coming from an ensemble of multiple normal distributions Qi, which then defines our proposal distribution Q theta. We calculate for each of the theta I an importance weight that is equal to the ratio between target and proposal distribution evaluation at that point, meaning the higher weight, point with a higher weight has a high likelihood of being in the distribution of the target, the P, and the Q of our proposal. And lower means that it's not in the target we're trying to approximate. Then, according to this weight, we choose these points with repetitions. Points with higher weight will be chosen several times. For example, here, the theta first has been chosen 3 times, and 2 other points were not chosen at all. And then we adapt the proposal distribution Q theta by setting these chosen points theta 1, 1, 1, 2, and 4 as its new locations. And then we have this mixture of Gaussian distributions with different weights. And finally, we can sample new points, a child population. Here, theta 1 has 3 children, as it was chosen 3 times. And this process can be repeated all over and over again, where children become the parental population, and then they create new children, grandchildren. So that's why it's called population Monte Carlo. In the end, the Q theta is supposed to be approximating P theta very well. But in order to make this whole idea work for online setting, we had to do many modifications. So the reason is that neural network weight state is evolving with every training iteration. So the loss landscape associated with these weights is also evolving over time. And then our target distribution is constantly changing. So first modification, we constructed a loss statistic that allows us to incorporate loss information from the old batches, from previous target distribution, from older out-of-date losses compared to the current neural network which we are trying to approximate each time. Next, we adapt the parameters, not every training iteration, but every P training iteration, and follow the changing distribution. And we do only one step of population Monte Carlo. We also use sliding window for constructing proposal and sample as many parameters as there are left from the compute budget because of the queue. And since the target changes, we use the latest information about the previous distributions. That's why we're using the sliding window, not all of the old information. And finally, we mix constructed proposal with uniform distribution, which helps to explore parameter space. There are 2 reasons for that. The first one is that initial sampling of the thetas is always uniform, so we might have missed some important regions about the distribution. And the second is that important regions might appear as the distribution changes. So everything is very dynamic. While in the PMC, the target distribution is one distribution, constant, fixed. I do refer you to the paper for more details. And let's take a look at the experimental experiments. So we conducted experiments for heat equation in a box with 5 temperatures, 1 inside and 4 on the side. And we have a fully connected neural network, which input is just 5 temperatures and a time step. And the output is a time step of the trajectory generated by these initial temperatures. While we don't see significant improvements in quality with breed, even though it's as good as the baseline, and it works, it is a work in progress. There are 2 very interesting insights. So first of all, for all experiments, we see that for breed, the training loss is always closer or even higher than validation loss. While for random choice of the parameters in online training, network shows overfitting for all the cases. And the second, breed does sample parameters which we assumed and wanted it to sample. There is a visible shift in chosen parameters distribution, input parameters, towards harder initial conditions. What I mean by harder, there are harder meaning the 5 temperatures values are more different, which make the trajectory more dynamic. So for example here, the first trajectory has very similar temperatures, so there is almost no dynamicity in the trajectory. And the second one has big difference in the initial conditions, so there is more dynamicity, and it is a harder sample, which breed tends to choose more. To conclude, online training is a key to connecting the HPC and surrogate training for science. And it is what allowed us to advance the training towards data efficiency with breed. And I invite you to scan this QR code or just follow the address below to access all the links for our previous publications, current publication, and the web page of Melissa with tutorials and contact form to send us an email if you want to use Melissa or collaborate or anything. Thank you very much.
Thank you. I think we have some time for a couple of questions. Okay, so I have one, Sofya. So in your, I think in the first test case you were talking, you do random sampling. And can you elaborate this one? How are the numbers changing as compared to your sampling approach?
In the baseline, basically. It is. So we have a queue of size n of the parameters we would run as a simulation to get the simulated data, and they will be just chosen uniformly in the range of parameters. For example, okay, if you have angle and speed, it will be between 0 and 90 degrees. Uniformly chosen possible parameter sampling, yes, and for the speed the same. So in some range it will be just uniformly chosen and run online. So both of the methods are online. But for the breed it will be updating what's next should be in the queue executed. It will not be uniform anymore.
Okay. So here on the right-hand side, they are somehow blue and red are.
Yeah, so as I said, so we conducted a lot of experiments for different sizes of the neural network in terms of both number of layers and size of the hidden layer. I do not show all of them because there are much more. But there are 2 cases where, for example, on the left, breed is much better, and on the right, it's significantly like almost twice worse. But the thing is that we see for the dotted line, which is a training loss, and the solid line, which is validation loss, for breed, in the worst case, it's on the same values. While we see for the red, the training loss starting to converge even more, so getting better, and validation loss stays the same. So there is a overfitting, and if we can continue to conduct these experiments, or if we do some harder experiments, it will be most probably even more visible. But we see this behavior for absolutely every experiment. We see that the uniform overfits very much because there are a lot of simple points, simple trajectories, so it overfits on the simple ones.
Thank you. Okay.
I do not hear you now.
Thank you for this talk. One clarifying question. When you have all your solvers running in parallel, that is per time set, correct?
Give me just a second. I have too many slides.
Yeah, right there.
So it is per... so one input parameter is one solver, so one is simulation.
Okay, thank you.
Or maybe I did not understand your question. It's okay. We can talk later.
Okay.
Is that all?
I think, okay, let's get the last questions here.
So quickly, you were placing samples where the loss was high, but that seems totally counterintuitive. If the loss is high, you're not interested in those function values. If the loss is high and you have high uncertainty, then you want to explore it.
Yeah.
But not if the loss is high. That you're minimizing loss, you're not maximizing loss.
So in the training, let's say, view, you kind of will minimize overall expectation of the losses because you have more density of samples near the higher loss points, and then you have more data for the neural network to train, and it will minimize this loss in the high ones. So you find the maximum, you sample more points there, so you by doing this, it goes lower, and then this region can be just forgotten or maybe re-explored again. But uncertainty is definitely our next step instead of the loss, but it's just not as easy to compute due to online. Yes?
Thank you. So we can move to our last talk. Okay. Yeah.